Hi, y'all. It's Ms. Blasky. Today we are going to smush together two of the topics from Unit 8. We're going to cover topic 8.2 and 8.3. So 8.2, we're talking about heats of reaction. This should be a little bit of review, hopefully, from Gen Chem. It's been a while, so we're going to go back over it. In order to figure out our enthalpies that we talked about last time, that delta H, we can do this experimentally. And so one of the ways we can do this experimentally is by using the idea of specific heat or heat capacity. So we have this measurement that we abbreviate with the variable C, which is known as the specific heat of a substance. And so the specific heat of different materials is different. Some can absorb a lot of energy before they start to change temperature. Some absorb very little energy before they start to change temperature. And that's what we measure with the specific heat. So the units on the specific heat are joules per gram degree Celsius. And so what that means is that the heat capacity is the amount of energy required to raise 1 gram of that substance by 1 degree Celsius. So just for reference point, water's heat capacity, which is very common and you'll be using it a lot, is 4.18 joules per gram Celsius. So water can absorb a lot of energy until it starts to change temperature. As opposed to most metals have heat capacities of less than 1 joule per gram Celsius. So we can use materials properties this way to our benefit. This is why we make pans, cooking pans out of metal, because we don't want them to absorb the energy. We want them to transfer that energy from the pan to the thing that we are cooking. We use water to help absorb energy, either to store that energy, if we're talking about solar energy, or if we're talking about trying to use that energy for something else, such as if you get into the swimming pool. The water itself is not going to feel the same temperature because it is able to absorb that heat more than other substances. So it is not going to have to transfer any of its sort of overflowing heat to the surroundings. So you can think of the specific heat as being like a little tiny bucket. Metals have a very tiny bucket. As soon as that heat fills up its bucket, it's going to overflow and start being transferred to the surroundings. Water has a pretty large bucket. It can absorb a lot of energy before it starts to overflow that energy and transfer that energy to the surroundings. So if we know the heat capacity of our substance, or our specific heat, we can figure out a variable called Q. So Q is the energy being lost or gained from a particular substance. So now this is not a delta H because we're not talking about a reaction. We're just talking about, hey, I have this chunk of lead and I'm going to heat it up. How much is its heat going to change? That's Q. Or hey, I have this bucket of water. How much is its heat going to change? That's Q. So Q is dependent on the mass of the substance that's changing temperature, its heat capacity, or its specific heat, I'm sorry, I keep saying that, is C, and its change in temperature. So delta T is the change in temperature. So final temperature minus initial temperature. Just like any other form of energy we're talking about, we have signs, positive and negative. If Q is positive, energy is absorbed by that substance, or it's endothermic. If Q is negative, then that substance is releasing energy, or it is exothermic. So this is pretty much just a plug and chug calculation. We can measure this heat by measuring the change in temperature. So notice that we are using temperature to calculate a change in heat. Temperature and heat are related to each other. They are directly proportional to each other, but they are not actually the same measurement. And this is a little weird. People get this confused a lot. But basically, temperature is our human made up variable to help give us a reference point for measuring changes in heat or changes in energy. Um, the energy itself is the amount of motion of those particles. Temperature is just our way of being able to vaguely measure that and represent that in a number. So chemists can measure these variables in a couple different ways. One way is called calorimetry. And we will be able to do a lab using calorimetry so that we can see how this all works out. There's a couple different ways that we can measure calorimetry. The way that we usually do it in lab is what's called a coffee cup calorimeter, which sounds sort of cheesy, but it actually works out really well. Styrofoam is a fantastic insulator. And so if you put two styrofoam coffee cups nested inside of each other, the air down in here between the two and then this double-walled styrofoam on either side is a pretty good insulator. It's not going to let much heat escape from the experiment. So if we have our thermometer down in here, we have a sample of water, which we know its mass. We can put a chemical substance in there, mix it into that water, see how much that water changes temperature. We could either have this happen because of a chemical reaction or just a physical transfer of energy. So for example, we could put two chemicals together that are going to react and measure their how much the temperature changes as they react. Or maybe we just have a heated metal piece and we put it in there and see how much energy transfers from the heated metal to the water. There's multiple ways to do that. The second type of calorimetry, which is not usually something we would do in a high school chem lab, is called bomb calorimetry. And it's called bomb calorimetry because the inside of the calorimeter looks sort of like an old-fashioned bomb, like those cheesy cartoon round bombs with a little fuse coming out the top. So the inside of it usually looks like that weird round shape. You can sort of see it sitting in here. Right there, they've got the lid off of it so you can see what's going on. Bomb calorimetry is usually used for not chemical reactions, but purely combustion reactions. So you place a sample of material inside of the bomb calorimeter and you light it on fire. By lighting it on fire, we know that we are breaking the bonds inside of that molecule or inside of that substance. And we are forming known quantities of carbon dioxide and water. And so by using a bomb calorimeter, we can figure out how much energy is inside of all of the bonds or intermolecular forces of that substance that we burned. When you look on the back of food products and it says how many calories something has in it for food, this is how they figured that out. Is they took that chip or they took that chicken or they took whatever food substance and burned it and figured out how much energy is inherent inside of all of those bonds of all the ingredients in your food. Once we know Q, which is the heat of just that substance, we can then transfer that into calculating delta H, or the enthalpy of that reaction or that chemical change, by saying that's how much heat we've used Q divided by the number of moles of substance that created that change in heat. So let's take a look at number 8. This is a fantastic question. Here we're talking about a chunk of metal. An unknown metal with a mass of 30 grams is in a beaker of boiling water at a temperature of 102 degrees Celsius. So let's sort of think about what this is going on. So I've got a beaker of super hot water. I've got a chunk of metal in here. And this is at 102 degrees Celsius. The metal is quickly moved, and we're going to pretend like no heat is lost as it is moved into a calorimeter. So here's our double-walled calorimeter with the thermometer down in there. We put that chunk of metal into that calorimeter. It's got 120 grams of water, which initially started at a temperature of 19 degrees Celsius. After a small amount of time, the temperature of the water in the calorimeter changed and stopped changing at 21.3 degrees Celsius. So then it says, what is the specific heat of the metal? So go ahead and take a minute and see if you can figure this out. There's a lot going on in this question. A lot of different temperatures, a lot of different numbers. Try to keep track of what everything is. So when I do these problems, I try and make a little chart or a little graphic organizer or something to help me keep track of what everything I know is. So I've got information about my unknown metal. I also have information about the water. So I know I have 30 grams of metal. Initially, it's at 102 degrees Celsius. And then I put it into 120 grams of water. Initially, its temperature is 19 degrees, and then the temperature of that water moves to 21.3 degrees. So now, cool thing that allows us to do this kind of math. If two substances that have different temperatures or different amounts of energy come in contact with each other, they can reach something called thermal equilibrium. Don't freak out just because it's got the word equilibrium in it. Equilibrium. All thermal equilibrium means is that these two substances are going to end at the same temperature. Once they've been in contact long enough, they can come to thermal equilibrium, which means that my metal is also going to have a final temperature of 21.3 degrees. They want me to find the heat capacity of the metal. I already know the heat capacity of water. This is a constant value. I believe it's on your periodic or on the back of your equation sheet. Is 4.18 joules per gram Celsius. So from all of this data, I can figure out how much energy change that water went through. So Q equals mc delta T. My mass is 120 grams. It can stay in grams. Heat capacity is 4.18 joules per gram Celsius. Change in temperature is 21.3 minus 19. So I can plug all of this into my calculator. Whoop. Pushing the wrong buttons. So 120 times 4.18. The difference in my temperature is 2.3 degrees. So I get whoa, I cannot use my calculator today. 2.3 times 120 times 4.18. There we go. That's better. So my Q value is 1,153.68 joules of energy. Now, that is going to stay positive because energy went into my water. Its temperature increased. So that has to be an endothermic process. Now, where did that heat go into the water from? Well, that heat had to go into the water from the metal. So my metal had to lose energy while my water gained energy. So for my metal now, its Q I already know. Has to be the same as the Q for my water, only the sign is going to be opposite. Because the energy went into the water, it needs to leave my metal. I know the mass of my metal was 30 grams. I don't know C, that's what I'm trying to find. My change in temperature now is 21.3 minus 102. So make sure that that is always final minus initial, not necessarily biggest minus smallest. So my temperature change is negative 80.7 degrees. So to solve for C, that's going to take care of my negative sign now. So if I do my calculation, sorry guys, my calculator's freaking out. Negative 1153.68 divided by all my other stuff from the other side, which is 2421. Gives me a C value. Now is where I sort of think about sig figs, just sort of in general. My C is 0.48. So the big idea here, we've got this idea of thermal equilibrium, that when two substances are in contact with each other for long enough, they can come to thermal equilibrium where they end at the same temperature. And then second idea, that however much heat gets transferred into one substance has to be the heat transferred out of another substance. Right? So there's a lot of questions. There's almost always one of these calculations on the AP exam. So I've given you a decent number of practice questions with those. With that same idea of how that heat is transferring from one substance to another, there's a whole bunch of different ways we can think about this. So you are going to see delta H or Q written in many different ways. But it's all sort of talking about the same idea. It's all talking about this transfer of energy. And it's all usually going to be written as delta H. But notice that each one of these has a little symbol down at the bottom or a little abbreviation, and it's going to tell you a little bit more about what's going on. So if you see delta H with an RXN down at the bottom, that stands for the enthalpy of a reaction. And so that's talking about an actual chemical reaction happening. Enthalpy of combustion usually has COMB after it, or maybe sometimes just COM. That is an enthalpy of reaction for a very specific reaction. That just means we're talking about a combustion reaction. Enthalpy of formation is with a lowercase f. We're going to be talking about this more later on this unit. That is very specifically the heat absorbed or released when 1 mole of a substance is formed from its elements. So that would be talking about like hydrogen plus oxygen making water. That would be we could figure out the enthalpy of formation of that water, thinking about the fact that it comes from H2 and O2. Enthalpy of fusion. This is talking about a phase change now. So these first three are all sort of more talking about chemical reactions. Fusion and vaporization, we are talking about phase changes. So fusion is talking about the phase change from solid to liquid or liquid to solid. So we're talking about intermolecular forces this time. And then enthalpy of vaporization with a little VAP at the end is talking about the phase change from gas to a liquid or liquid to a gas. Now I'm saying both phase changes because it's the same phase change. If one way requires energy, the other way is going to form energy, depending on which phase you're changing from. So we can look at these state of matter phase changes a little bit differently. So we can think about phase changes as talking about the breaking or forming of intermolecular forces. So this is very different from chemical reactions, but we have a sort of more general pattern to how this works. Now I know there's a lot of writing on this picture, and you might want to keep this one up because it's got all the color coding on it, but we've talked about these phase change diagrams in Gen Chem. And we're going to just sort of compare that to what we know now. So at the lowest energy, the lowest temperature, we usually have a solid. If we add more energy to that solid, we are going to increase its temperature until we hit this magical point called the freezing point or the melting point. Means the same thing. At that particular temperature for that substance, if I keep adding in energy, that energy is going to be added in to break apart the intermolecular forces holding those atoms or molecules together. So we have a change of what that energy is being used to do. At first, that energy was being used to increase the temperature. Now that energy is being used to move particles around. Once all of those particles have their intermolecular forces broken up and all have turned into a liquid, then any additional energy added to that system is just going to increase the temperature of those liquid particles. As we increase that temperature, we're increasing the molecular motion, which means my kinetic energy is increasing. Again, I hit a particular point where now I have enough energy to, again, break apart any additional intermolecular forces that exist there. I'm going to break apart all of those remaining intermolecular forces until I form all of those particles into a gas. We now have increased the energy of those particles enough that they all have separated, all have broken all of their intermolecular forces. And again, any additional temperature I add or any additional heat I add to that system is going to increase its temperature, increasing the kinetic energy of those gas particles. So we can see how different steps occur when we go through these phase changes. So these questions down below, questions 1 through 9, are really fantastic to sort of think about those changes in phases and what's going on. So thinking about these phase change diagrams and what is going on at each particular point in a phase change is a very important thing that shows up a lot, especially on the multiple choice of the AP exam. So we will come back to all of these ideas of these different types of delta H's. We'll refer to them throughout the rest of this unit. So I'm going to stop here at the end of section 8.3 for right now, and we'll carry on next time. See y'all later. Bye.